All right, so going through these problems here, for question number 1, you have a rotating spacecraft. It has 2 rings, an outer ring with radius r0 or r0, and then an inner ring with radius ri. The outer ring mimics the surface gravity of Earth, so at that point there, you would feel an acceleration of gravity like Earth's, which is g. And the inner ring is designed to help the astronauts become accustomed to a new planet which has an acceleration of gravity or field strength that is g over 2. First thing is to derive an equation for the speed of the outer ring in terms of r, o, and g. So in this case here, we're still talking about something that's moving in a circular path. So the force that any point in that outer ring would feel would be towards the center, equal to centripetal force. That centripetal force would be equal to the normal force, which, if it's mimicking, just sort of being on Earth, so a person just kind of standing on Earth, that normal force would then have to be equal to the pull of gravity, so mg. So really the acceleration that they're feeling should be the same as that it is on Earth, which is g, right? So the acceleration here in that outer ring, centripetal acceleration it should be equal to g. And so we can set the equation for centripetal acceleration, which is v squared over r, equal to g, because the acceleration is little g. And so we're just going to solve for v in terms of these other variables, right? So v0 or vo squared over ro is equal to g. And to solve that, we move the r over to the other side. Right, that cancels out r on the bottom of the fraction. And then we're going to square root both sides. So we're going to square root both sides like this. So your final equation for VO should be equal to the square root of g times RO. Next, we're going to derive an equation for the spacecraft's period of rotation in terms of RO and g. Right, so we have this velocity here. We also know that velocity, when we're talking about something in a circular motion, is equal to 2 pi r over the period, right? So the period's involved there. The reason I know to use this is because I'm looking for an equation that has the period in it, right? And so far, this is sort of where all our period equations originate, is from this expression of velocity, right? And then usually we take this expression and plug it into something else. So always keep this in mind. This is not something that's generally given to you, so you do have to kind of memorize it for an object moving in a circular orbit. 2 pi r over t is our velocity. We're going to set that equal to our velocity up top, right? So we're going to set that equal to that VO, so which means 2 pi r o over period should be equal to the square root of g ro. And so I'm going to solve for the period here. What I'm going to do is I'm going to move t over to the other side, and that eliminates the t on the bottom there. And then I'm going to divide both sides by the square root of g ro. Okay, so what happens is that it eliminates the square root of g ro on the right side, and so I just leave t by itself there. So I have t is equal to 2 pi ro over the square root of g ro. So I have ro on both parts of the equation here, on the top and the bottom. It's actually ended up being 2 pi the square root of ro over g. Okay, so this is how I would simplify it. So that's my expression for the period in terms of r's o and g. Okay. Next is I want to determine what the radius of the inner ring would be relative to the radius of the outer ring. What I know about the inner ring is that it has to have a speed, an acceleration of g over 2. That's the experience it should have, right? That the person in that inner ring should feel, which basically means that my acceleration should be g over 2, And so I could go back to my original equation, just kind of rederive everything, but instead I'm going to use this expression here, right, to kind of figure out what it is that I need to figure out. So I know that t is equal to 2 pi square root of r over g, right? I also know that if this whole thing is spinning, right, if I pick a point on the outer ring, the time it takes to go around once is the same time it takes to go around once for the inner ring. So the period is the same for the inner and the outer ring, right? So t really is a constant value. And so what I'm going to do is I'm going to re-express this in terms of what r has to be relative to g, right? So I'm going to solve for r in this expression. So I'm going to divide both sides by 2 pi. And then I'm going to have t over 2 pi on this side is equal to the square root of r over g. I'm going to square both sides. So I have t over 2 pi squared is equal to r over g. And then I'm going to move g over to the other side. So this ends up being that t over 2 pi squared times g is equal to r, right? If I plug in g as in the value on Earth, right, then r here would be r0, or r out, basically, right? Because if I want the acceleration of gravity to be equal to the one on Earth, then the radius of the ring has to be r0. But instead what I wanted is I wanted to be half of that. So really what I want is this to be t2 pi squared g over 2, right? And what does that equal? Well, that should equal ri, the inner ring, right? Basically, if you look at this expression here, and compare it to this original expression, the only difference is that there's a factor of 1/2 in front of it, right? So it's 1/2 times t over 2 pi squared times g. That's the same expression we had in that original equation. So really, ri is just half of ro. Okay. So that's basically what I'm trying to figure out, is what that value of ri is relative to ro, and it has to be half the radius of ro.